we're going to take a look at Hooke's law here, which is kind of governs, at least for us, simple springs, the only kind of springs that we're going to care about here. So Hooke's law, it describes the force exerted by what we call an ideal spring. And Hooke's law is that the spring force, or the elastic force, is equal to negative k times delta x. And delta x is the change from the rest, or if you want to call it, the natural length. So if nothing was pulling on the spring, and the spring was just sitting by itself, how long is it? Hooke's law says if you change the length from that by a certain amount, you'll get this force. The spring will exert this kind of force. So this k right here is the spring constant, is what we call it. That's looking real ugly. Let me clean that up for you. Spring constant. And the spring constant is just a fancy word for the stiffness of the spring. So if you think about it, if a spring is stiffer, it's going to exert more force, right? If it's harder to pull on a spring, that's because the spring is resisting more. If it's harder to compress a spring, that's because the spring is resisting more. It's stiffer. If you've ever seen the springs that they use for shocks in a car, it's really hard to push those. They're very stiff. And you want them to be stiff because you don't want that those springs to compress and bottom out. You don't want them to compress as much as they possibly can. You want them to resist the bumps and the bounces and the rows. So an ideal spring is what was listed up here. And this is a bit of a circular or maybe tautological definition, but we say that an ideal spring is one that actually obeys Hooke's law. So what is an ideal spring? It's something that obeys Hooke's law. What is Hooke's law? It describes an ideal spring. So it's just this fancy class of simple to examine springs. And that's what Hooke's law is let's think of the simplest way that a spring could work, and that's Hooke's law. And then it says, okay, any springs that are simple, they're this simplest form, those we'll call ideal. So most springs are ideal for small, is there a word that I'm looking this? I do not know what word I was trying to write, but that one's not going to work at all. Small, small changes in length. So if you just stretch it a little bit or compress it a little bit, most springs will obey Hooke's law. And if we look at Hooke's law, that f of s equals negative kx, you'll notice if I were to make the spring longer, in other words, if I were to stretch it in the positive x direction, which direction is the spring going to pull? In the negative direction. If I compress it and pull it in the negative x direction, then the spring is going to push back in the positive direction because of that negative sign. And that's a key factor in Hooke's law, is that it always resists motion away from that natural kind of baseline. And so that is known as a restorative force. Because of that negative, it is a restorative force. It is trying to bring the system back to how that natural position is. So again, compressing a spring, it's going to want to push out. Stretching a spring, it's going to want to pull in. It's going to want to go the opposite direction that that the outside force kind of affected it. Okay, let's look at an example here. A spring is hung from a small stand and measured to have a length of 15 centimeters. Next, a 500-gram weight is hung from the spring stretching it to a new length of 20 centimeters. What is the spring constant or the stiffness of this spring? Well, what we know is when we're hanging that weight, it has a downward force of Fg equals mg. If it's just hanging there, then that means it also has an upward force that's equal. But we know that that upward force is the spring force, which should equal negative k delta x. And we know that Fs plus Fg has to equal 0, so therefore Fs equals negative Fg. But that's wrong because that should be a minus because it's pointed downwards. So Fs equals Fg. Sorry for that lack of clarity. So negative kx is equal to mg. Now our delta x is going to be how much we stretch this by. Well, originally it was 15, and then it stretched to 20. So it's going to be 15 centimeters minus 20 centimeters. Because, you know, if we think about, that's not a good way to present it. I'm getting ahead of myself trying to get the right signs in, but let's talk about it. Final minus initial, so 20 minus 15. Delta x equals 5 centimeters, but it's 5 centimeters down, so it should be negative. So in other words, this whole expression here should have been negative because we were going in the downwards direction. So we get negative k delta x is equal to mg. We get k is equal to negative mg over delta x. So we get k is equal to 500 grams times 9.8 meters per second squared over negative 5 centimeters. So now we've got a problem because these units aren't the same, so we'll have to convert this into meters and into kilograms. Because remember, kilograms times meters per second squared is going to be our newtons. And so we will get k is equal to 0.5 kilograms times 9.8 meters per second squared divided by negative, sorry, should be negative on top and bottom, negative 0.05 meters. Work all of that through and you'll get some answer, and then the units we use for spring constant is newtons per meter. Because we want to think about it kind of like how many newtons is required to stretch this spring by 1 meter. And so that's why we write that in those values. You're going to get roughly, actually no, we can do this pretty easily because 0.5 divided by 0.05 is 100 times bigger, and 100 times 9.8 means we get 980 newtons per meter. So that's our spring constant based on this problem.